everyone, and welcome to this episode of Foundry Fireside. My name is Sydney, and I'm an intern on the Foundry Communications team. Today, I'll be chatting with one of the Foundry's postdocs, Maher Alghalayini. Welcome, Maher. Could you please introduce yourself?
Hi, Sydney. Hi, everyone. I'm a fourth year postdoc here at the Foundry. I work with Carolin Sutter-Fella in the inorganic facility, and I also work with Marcus Nowak from the Center for Advanced Mathematics and for Energy Research Applications, short camera. And the main motivation of my work is that basically the way materials are designed and synthesized, they affects their performance. And usually, designing these materials require many parameters to be tweaked, to be chosen, the values set in order to get a good performance out of those materials. So the main umbrella of my research is that how do we efficiently design these materials via closed loop active learning approaches using machine learning and AI. And I I worked on multiple applications during my PhD. I worked on additive manufacturing. I came to the lab. I worked on batteries and predicting battery failure. And now I'm working on efficiently exploring, like with the fewest possible experiments, the synthesis parameter space of perovskites and other materials used in in optoelectronics and semiconductor applications.
Thank you. Can you explain machine learning to someone who has no experience with coding?
Machine learning at its heart is just about finding relationships between variables. These variables are like things that we can measure or we can control. And trying to understand how they connect. So, for example, think about it cause and effect. We want trying to recreate this relationship, and basically, like assume we are trying to predict or to identify the price of a house based on its size only. So basically, as size of a house increases, the price usually tends to go up. But then there are also like as you can know that there are other parameters, like for example, the neighborhood, the state, um, taxes. I don't know. That all affects how the prices are set. And machine learning is just we allow like the computer to discover these relationships from the data. And part of machine learning is also trying to understand like what are the experiments that we should be doing in order to get this relationship. Because yes, we can find the relationship if we have the data, but what if we want to collect the data? And then this is basically the part I find most exciting, like identifying what are the experiments or what's the data that we should measure. Because basically you can measure or you can collect the data for all the houses that you have, like I don't know, in the region, in the state, and the country, or you can collect some of them, and based on those you can create this relationship. Because basically, if we want to do all possible combinations, all possible houses, that's going to be expensive. It's going to be slow. We're not going to be able to get all this, all the like actual relationship very fast. And we can say like if the relationship were simple, like straight line, assume for example, like the cost increases with the size, then we can just collect 2 points or two houses. We see look at two houses and then we can find this relationship. But real life is messier. Is messier than that. So instead of checking like everything, I would use AI to identify what is the next set of experiments, what are the measurements that I should be doing, so that we can get the most informative experiments as possible. And in my work, basically the houses what you're talking about are the materials, and the house size is the material synthesis parameters, and the measurements here are basically expensive and costly and like time consuming. So being smart about what to do, what other experiments to do next, um, can and would save huge amounts of time and money.
Wow, that's really interesting. So, what does it mean for the AI to choose these experiments, and how is the AI making these decisions?
So So basically, researchers traditionally they have been choosing experiments based on their experience, their trial and error, which is basically known as the Edisonian approach. But this is not efficient. Like, the light bulb took Edison more than 70 trials um, to get it working. But in this fast-paced world, we cannot afford this anymore. We use AI to identify the most informative experiments for us to do. So basically, what it chooses depends on your goal. So when we say AI chooses the experiments, it depends on what is the goal the researcher or we are trying to do. So, for example, am I trying to get the best performing material, or am I trying to understand what is the effect of process parameters on the performance of the material, or am I trying to understand both? So basically, the AI will look at everything we have measured already. Like basically, this is a closed loop. It means that we do experiments, we learn from them, we choose another set of experiment to do. And now here, at any point in time, AI would look at all the experiments that we collected, all the data that we measured, and we figure out what is the where in the parameter space or which experiments that we are most uncertain about. Like we don't know information about, and then it would do experiments there. Or for example, it's gonna tell us, it's gonna look at like where do we have the biggest uh, opportunity to improve on our performance, and then it's gonna steer us towards that direction. And then this, instead of guessing, it will allow us to run the experiments that sort of like most informative for us. And like upon your question, like how does the AI make the decision? Well, basically, it runs the so-called acquisition function. It's just this acquisition function is it's how we define the objective to the computer. Like basically, we tell it, for example, give me the location or give me the experiment that you are most uncertain about. So the acquisition function is basically looking at the amount of uncertainty that we have, like for example, in terms of experiments, and finding which experiment that we don't know, like we have the maximum uncertainty, and it's gonna choose that experiment. Is what
That's really interesting how the AI is able to identify the experiment. So, what made you interested in pursuing this area of research, and what keeps you interested?
So basically, my very first class in undergrad was the material science class. It used to be a second year class, but I took it. And from the first hour, basically, I got interested in how like materials are synthesized, and then the idea is that the way they are synthesized, they would behave, and it got me thinking like, how can we improve them? How can we make things better? Because eventually, like engineering, I was like first year engineering student, proud engineering student. We need to make things better. And then I learned that many conclusions, like in material science and in general, basically, many conclusions are actually are based on one or two or few experiments. Um, they do an experiment, they come out with a conclusion, and they stick with it. But as we said, like life is messy. Like if you can repeat the experiment 100 times, you will have 100 different results. They can be similar, they can be close, but they are different. And th- that also got me into thinking about, okay, so we should be looking at distribution, we should be looking at statistics in material design. And that's where throughout my undergrad, my master's, I got this statistics background, and then in my PhD, I decided to combine them, material science, mechanical engineering, and statistics and math. And I came up with material design, optimizing material property, and that's where I'm still.
I like how you're able to combine your interests to find the right path for you.
Yes, thank you. Yes.
So, what goes into creating this type of AI?
So in order to create this type of AI, basically, of course, coding experience is required because you have to tell the computer somehow. like what is the problem that you are trying to do? Like what is the objective? For example, what is the input variables? Like is it the house size, the house neighborhood, for example? And what is the output? Or what is the thing that you are measuring? Is it like the house? It could be, for example, the house cost. And it also requires understanding the statistical methods that that are related or corresponding to those materials, corresponding to those methods that we are using. So, for instance, I use a Gaussian process model, Gaussian process modeling, and Bayesian optimization, and these are statistical methods, meaning that they are like they have equations based on statistics, based on theories from statistics, and the user of these methods should have at least like an introductory understanding of what is the distribution, what is the standard deviation, what is uncertainty, what is certainty, for example. And because of these methods are basically the predictions are sort of equations that one would evaluate. So these equations, one can write them from scratch, but we don't have to reinvent the wheel. We can use already written packages from people who already like publish them. So for instance, like these packages, like these are just set of functions that run together, and they are like general enough that can be used for any type of application, whether it's material science, whether it's biology, whether it is medicine, for example. Like it can be general as possible. And then, so for example, I use the GPCam package, which is a package that came out from the lab, from camera, and I just run those codes, and I get my predictions and run them.
Wow, that's really interesting how you're able to combine physics and these code packages to run these AI models. What's the most interesting application of this research that you've worked with so far?
So throughout my PhD and my postdoc, I worked on multiple applications for the same method, but multiple applications. But they each have their own set of challenges, each set of rewards. But I have two projects actually, like they are most rewarding for me. The first one is working with perovskites and doing experiments on synthesized using like robotic arm. It's the robot arm, the Autobot that we have on in the inorganic facility. It was basically we have like I would tell the robot, or like I would tell my collaborator who was working on the robot like what are the experiments that I want to do, and he would do them and characterize them and give me the results in order to give him the next set of experiments. So this was sort of semi-autonomous experimentation, if you want. And like the reason why I feel like it was rewarding for me, because it was like I saw that my work, like my chosen experiments, the outcome from my work has real direct effect on the progression of the experiments. If I chose wrong experiments, then basically we have wasted some experiments. Or if I chose something that's like okay, it could be informative, couldn't be informative. I would see that the models wouldn't improve, or the GP or um, the predictions wouldn't tell us what we want to predict. So the other experiment is basically is which I'm recently working on. I recently finished is a fully autonomous experimentation where we had a robot also. Um, it's in the inorganic facility also, but that robot could do all the experiments on its own. It chooses the experiments on its own, do the experiments, characterize them in situ, and then it chooses the next set of experiments. And for that robot, it was also in-house built here in the foundry. It was based on Python coding, so basically we could tell it what are the experiments that it wants to do, what are the parameters that it should choose, and then it can do them autonomously. So the nice thing there, I just integrated my codes into this robot, and I just saw it running, on its own without human intervention. And then he's like, "Don't tell me what to do. I know what to do. And I'm gonna do those experiments." Like, okay. And it was great seeing that happening, in real time, doing the experiments, choosing the next set of experiments, and like doing 100, 200 experiments in a day. So that was a huge wow for me. So yeah.
That's really rewarding to see your work come to life. So, how is this AI going to be used in the future to make scientific research more efficient? And what's the hope for this research in the next 10 to 20 years?
So the core idea is basically the shift from trial and error, like the Edisonian approach, to guided discovery. Even though people have started doing like materials discovery using robots and using AI, it's just like there's a lot of materials discovery are still happening using the old way. Researcher has an intuition, experience. For example, from experience, they would run the experiment, they would look at the results, and they adjust the results. Now, the problem is that the space of possible materials is astronomically large. There are many variables that we can change at the same time. Like for example, you have the composition of materials, the temperature, processing conditions. This results in a very large number of combinations that one could possibly do experiments at, but by hand, it's just like it's not feasible. So what the AI does is just act as an intelligent guide to tell us through this space, to tell us where to do experiments. Like that, do we have to do all possible experiments? I mean, of course not. Okay, so what we need to do subset. How do we do that? Which subset do we do? And it's basically for the 10 to 20 years vision, I think the dream basically is what's known as the self-driving labs. People have started also looking into this, but I think it's still in its infancy. Self-driving labs, these are basically the AI would propose what experiments to do. It sometimes also proposes what is the hypothesis that should be tested. Um, in order to do something. Like, so of course we would have an objective. So based on the objective, let's say for example, give me a better material for aerospace, for outer space, for example. And then the within this big objective, there is there are many hypotheses that one could test. Like, do I need a higher tensile strength material? Do I need, I don't know, do I need more higher hardness, for example? Those are very specific metals properties. But these are like hypotheses that one could test how to get to that bigger goal of, oh, give me materials for outer space. And self-driving labs, I think they should be able to do those hypotheses to identify what is the actual hypothesis that we need to be testing, and it runs those experiments on its own. Do that, get the experiment, get the results, get the feedback. Do also like keep repeating doing the experiments, and then come out with the conclusion of like, how can I solve the hypothesis that it came out with, and is the hypothesis that was tested was really the correct question to ask, or should we ask another question? And this basically is not, of course, this is not replacing scientists. Like we don't want to replace scientists, but it's basically we are trying to free them from those lower level applications or lower level um, experiments or tests or you know um, jobs, if you want, because this is all slow, repetitive search, and we can basically make the scientists focus on what is like more abstract application, if you want, like more abstract thinking of ideas, something that AI still cannot do.
I'm excited to hopefully see these self-driving labs in the future. Those are all the questions I have. Thank you so much for meeting with me. It was really interesting to learn about your research.
Thank you for having me. Thank
For those of you watching, you can learn more about the Molecular Foundry by tuning in to more episodes of Foundry Fireside.